Have you ever wondered what happens when scientists run a huge experiment, expecting to find something incredible, and instead, they find, well, nothing? It's like a mystery novel, and today, we're going to learn how to solve it.
I mean, seriously, why? You can have this brilliant theory, you run the study just right, and the results still come back completely flat. So, what's going on? Why do some experiments just find nothing? Let's get into it.
To figure this all out, we need to put on our detective hats. That's right, for the next few minutes, you are the lead investigator. Your mission, should you choose to accept it, is to examine the evidence and uncover the real story behind these so-called missing effects. Okay, first things first, every detective needs to know the lingo. The official term for finding nothing is a null result. Basically, this just means there's no statistically significant difference between your groups. You'll know you've got one when the p-value is bigger than 0.05 or when that 95% confidence interval actually includes 0, which means no difference is a totally plausible outcome. Now, this is maybe the most important clue of all. When you get a null result, it's so easy to think, well, I guess the theory was wrong. But that's not what it means. It doesn't mean your idea is junk. What it might mean, and this is way more common, is that the study just wasn't sensitive enough to actually find an effect that might really be there. It's not about the theory, it's about the investigation itself. All right, so if we're investigating the investigation, where do we even begin? How do we break this case down and figure out what really went wrong? Well, turns out our whole investigation comes down to just two main questions. And here's a great way to think about it. Imagine you're trying to tune an old radio. First, you have to ask, was the signal strong enough? That's the music you're trying to hear, the difference between your groups. But then you also have to ask, was there too much noise? You know, all that static and fuzz? If the music is too quiet or the static is way too loud, you're never going to hear the song. That's our framework right there. So let's start with that first line of inquiry. Let's look for clues that maybe, just maybe, the signal itself was just too weak to pick up. All right, we've got a couple of usual suspects here. First up is what we call a weak manipulation. Think about it. If you're testing a new drug and you compare a 1 milligram dose to a 2 milligram dose, that difference is probably way too small to have any real effect. The signal is weak right from the start. The other suspect is an insensitive measure. This is like using a simple pass/fail system to see if a new teaching method works. A student could go from a 68 to a 78. That's real improvement, but your measure just sees pass both times. It's not detailed enough to catch the change. And then you've got these two troublemakers, ceiling and floor effects. A ceiling effect is when your test is so easy that everybody scores at or near the top. If everyone's already acing it, there's literally no room to show improvement, right? A floor effect is the exact opposite. The test is so brutally hard that everyone scores near 0. In both cases, the results get all squished together at one end, completely hiding any real difference between your groups. Okay, but what if the signal was actually fine? That brings us to our second prime suspect in this case. What if the problem wasn't the music, but the static? Was the statistical noise just way too loud? This is the absolute heart of the matter. If there's too much random chaos, too much variability within each of your groups, it becomes impossible to see the clean, systematic difference you're looking for between them. The signal gets completely and utterly lost in all that noise. So where does all this noise come from? Well, the biggest source by far is just individual differences. I mean, people are just different, you know? Some are in a better mood, some are naturally better at a task, some had more coffee. All that natural variation creates a ton of statistical noise. The easiest way to spot this is to look for really big standard deviations in your results. The fix? You either need a much bigger sample size so that all that randomness can average itself out, or you can use a clever design where each person is their own control. Next up, you've got situation noise. This is all about the research environment itself being messy or inconsistent. Just imagine trying to run a memory study, but half your participants are in a quiet room while the other half have loud construction going on outside. That's a huge distraction. It adds a bunch of random error that can easily wash out a real effect. The key here is simple. Standardize everything. Make the environment exactly the same for everyone. And our final noisemaker is measurement error. This is when the tool you're using to measure things is just a bit off. You know, a stopwatch that sometimes glitches, a survey question that's kind of confusing, anything that adds random fuzz to a person's score is measurement error. The best way to fight this is to use really reliable, super accurate tools.
and sometimes even take a few measurements and average them together.
All right, detective, you've learned the techniques, you know the usual suspects. Now it's time to put those skills to the test. Let's crack a sample case together. Okay, here it is, the evidence file. The research question, does classical music help people do better on math tests? We've got our two groups, music versus silence. We've got 20 people in total, and the result, a p-value of 0.89. Woof, that's a classic null result. So, detective, what went wrong?
Let's run our checklist. First up, the signal. The manipulation, music versus silence, seems fine. The test goes up to 50, so probably no ceiling or floor effects. So far, so good. Now let's check the noise. And whoa, look at those standard deviations, 12.3 and 11.9. They are enormous. That's a huge red flag for massive individual differences in math skill. And this leads us to the final problem, power. With only 10 people in each group, the study had almost no power. The sample is just way too small to cut through all that noise.
So our final verdict is in. We didn't find an effect, but probably not because music does nothing. It's because any tiny signal that might have been there got completely drowned out by the noise from everyone's different math abilities. And the study was just too small to find it. Case closed.
See? You cracked it. Now, let's get all of these tools organized into your official Detectives Toolkit so you're ready to diagnose any null result that comes your way.
And here it is, your complete diagnostic checklist. It's a two-pronged attack. First, check the signal. Ask yourself, was the manipulation weak? Was the measure insensitive? Were there any ceiling or floor effects? Then you pivot and check the noise. Was there too much random chaos from individual differences, situation noise, or bad measurement? And wrapped around all of it is that one crucial question. Was the sample size big enough? This checklist is your key to cracking any case.
And that really brings us to the big takeaway here. A null result is not a dead end. It's not a failure. It's a clue. It's telling you that if an effect is real, it might just be hiding. And that challenges us to be better detectives, to design smarter, stronger, more powerful studies that are actually good enough to find it.